Mr. Tarrou, in this calculus lesson, we are going to be doing 4 examples involving trigonometric substitution. We are going to run through the 3 situations or scenarios that we'll have with these type of problems. We're going to, as we work through these 4 indefinite integration problems, look at how some of the expressions that are in these integrands are going to look similar to when we were integrating inverse trig functions or dealing with those type of functions. And I'll remind you of those 3 integration rules as we go through our examples, so you see a little compare and contrast. I might actually include a 5th example, depends on the length of the lesson as we go through the 4 examples that I prepared for us. And by the way, the preparation of this video, I've been teaching high school for 20 years, and a few years ago I got the opportunity to teach calculus for the first time and brush off and relearn those skills that for calculus that I had to learn in college to get my math education degree. Well, I've really enjoyed the process, and so I'm extending that now into concepts beyond what I get to teach in high school and allowing YouTube and you guys to, give me inspiration to brush off these old skills, relearn these old concepts, and prepare lessons for you. So I've gone through the textbook and, read it and watched other people's videos on YouTube and worked out the lesson and prepared my own notes based off of that were inspired by the types of questions that were in my textbook. So you're going to get a real good detailed set of notes and worked out examples to help you understand this concept for the first time as well, I hope. So for integrals involving the square root of a squared minus u squared, we're going to let u equal a times the sine of theta. And then we have the square root of a squared minus u squared is equal to a cosine of theta, where theta is between negative pi over 2 and positive pi over 2. And these restrictions on theta are coming from the restrictions that you learned back in pre-calculus or trigonometry when you were studying, just inverse trig functions. There may be a time in these problems where you have to use this original substitution for u equals, a sine theta or u equals a times tangent of theta, and work out an expression or a substitution for specifically theta, and that's where these restrictions on theta is coming from. It's working with those inverse trig functions such as the inverse sine and the inverse tangent. We're also working with these trigonometric substitutions, basically the reference triangles that used to set up between the terminal side of an angle in standard position and the x-axis. So we're looking at right triangle trig, and when you see the square root of a squared minus u squared, a is going to be a variable representing a constant, and u representing a variable or a variable expression. Of course, when you have that a squared plus b squared equals c squared, and you start working out expressions that give you the lengths of a leg, the hypotenuse has got to be the longest side of the right triangle. And you can see that with a squared minus u squared, you can assume or conclude, not assume, that a is going to be the length of the hypotenuse and u is going to be the length of one of the legs. And we'll talk a little bit more later about how we place those variables, especially that variable of u, on one of the legs of that right triangle, unless of course it just happens to be the hypotenuse. So for integrals involving the square root of a squared plus u squared, we're going to let u equal a times the tangent of theta, and then the square root of a squared plus u squared is going to be equal to a times the secant of theta, where theta is restricted between negative pi over 2 and positive pi over 2. And that, I believe, as I read this out loud, should not have equal signs here. So I do apologize for the copy error. Now, why is it that with this second rule we need to restrict theta to be between negative pi over 2 and positive pi over 2? Because if we need a substitution for theta, then we're going to need to base that off of the inverse tangent function. And when you do inverse tangent, or just work with the tangent function, tangent is undefined at pi over 2 and negative pi over 2 because tangent's y over x, and if you rotate pi over 2 radians, or 90 degrees, the x-coordinate is going to be equal to 0, and tangent will be y over 0, and thus undefined. So those equal signs there, well, they shouldn't have been. So let's take care of that. Sorry about the mistake, or the copy error for my notes. Now we see that we have, for integrals involving the square root of a squared plus u squared, well, we have basically what? A, u, and the square root symbol are supposed to be representing the sides of a right triangle. And so when you have two sides of a triangle squared and added together, And the square root of that expression, well, that's going to be the hypotenuse. So we have the hypotenuse being the square root of a squared plus u squared, and then a being one of those legs, and tangent, u being the measurement of the other leg, the square root of each of those squares. Now over here, for integrals involving the square root of u squared minus a squared, let u equal a times the secant of theta, then the square root of u squared minus a squared is going to be equal to a times the tangent of theta if u is greater than a, where theta is between 0, greater than or equal to 0, and less than pi over 2. And negative a tangent of theta if u is less than a, where theta is now greater than pi over 2 and less than or equal to pi. These restrictions on theta are coming from the inverse secant function. Inverse secant is the reciprocal, of course, or is equal to 1 over cosine. So the restrictions on inverse cosine being between 0 and pi are going to be very similar to the restrictions we have on inverse secant, of course, except secant being r over x, again, is going to be undefined at pi over 2, and thus we need to remove that pi over 2 in our restricted domain or values for theta. Now, I worked through the entire section involving these problems, all the mechanical type questions involving these type of problems in the section, and I didn't come into any issue where we had to deal with, or had to deal with this negative a tangent of theta if u is less than negative a, where theta is between pi over 2 and pi. So I've seen in lessons where this restriction is going to come up later on in our calculus studies, later on in the book, so we're not going to worry about that in this particular video. If we have the expression of the square root of u squared minus a squared, then this variable expression of u is going to represent our hypotenuse, and then a is going to be one of the legs, and therefore this square root of u squared minus a squared is going to represent the other leg of this right triangle. We're going to be setting up our trig substitution by using the right triangles, these reference triangles, again, like we saw in pre-calculus and trigonometry, where it was against the x-axis, when we see a square root of a sum or difference of squares. Okay, well, let's talk a little bit about where we place, why is it I'm putting the value of u on this vertical leg, or why is it here also on the vertical leg, but over here, how do we know that the constant of a is going to be a leg and the square root is going to be the vertical leg? Okay, well, that's going to come up right here. Some step-by-step instructions that are a little bit in more of a plain English type idea. We're going to set up the sides of a right triangle with the sine of theta is equal to u over a, the tangent of theta is equal to u over a, or the secant of theta is equal to u over a. So our initial setup with our measurement of theta is going to be our expression of u over a, and notice that a is the denominator of each of these ratios. And also note that the sine, tangent, and secant. Now think about the 6 trig functions that we learned in trig and we've been working all the way through in calculus. We have sine, we have cosine, we have secant, we have cosecant, we have tangent, we have cotangent. So 3 of those names start with CO, or they're kind of like they're co-functions. So we want to set up this substitution working with a ratio of theta using one of the primary trig functions, the sine, the tangent, or secant. Now, if you look over here, recognizing that we have a hypotenuse length and a leg length, I know that's the hypotenuse because it's the first term in a subtraction, and I want the difference there to be positive. Where do I put the a? Well, I'm going to set up a ratio from theta. It's going to be one of the 3 primary trig functions, and I want the denominator to be the constant. Okay, so if I put the u down here, then I would have the cosine of theta is u over a. But I don't want a co-function, I want a primary function. So if I place my u here, then the sine of theta is u over a, or opposite over hypotenuse. With those integrals involving a squared plus u squared, and recognizing that I have the sum of 2 sides squared and added together, so thus the square root has to be the hypotenuse, does the u go here, or does the u go into the horizontal leg of this triangle? Well, if it was u and a, and I needed to have the constant be the denominator, then it would be the cotangent of theta is adjacent over opposite. Okay, well, I would have a constant as my denominator, but I would be setting up a cotangent function, not a tangent function. So if I need to use one of the primary, or if it's suggested that I use one of the primary trig functions, then the tangent of theta is opposite over adjacent. And that's how we're thinking about as we set up these little right triangle diagrams to help us to basically eliminate all the references of x in our integrands and replace it with references of theta. Great. And that's how these u's and a's and the square roots are getting placed around those right triangles, is this first step that we're going to follow as we do these problems. Then we're going to find the derivative of u. So we're going to say that, as an example, the sine of theta is u over a. We'll move the a over and then find du. We're going to find a trig substitution to eliminate the square root, the radicals that you see around these right triangles. We're then going to integrate, and then finally we're going to substitute back into the terms of our original variable, and that is going to be the 5 steps we are going to go through to do these 4 examples involving trigonometric substitution. First example coming up right now. For our first example, we are going to do the indefinite integral of the square root of 25 minus x squared over x dx. Now this isn't a really close integrand to maybe something that we've integrated before, but we will see some similarity in the appearance of the integrands in this particular section that we're studying and our inverse trig function rules, integration rules that we had and that we worked with in an earlier chapter, where we have in this case the indefinite integral of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c. And, you know, we do have a radical or a square root with a difference of squares in here. So we can see how it's easy to get, you know, looking at these integrands now where we're doing trigonometric substitution and get a little bit confused, or maybe possibly think that we're going to use some integration rules that we've been able to use earlier. And we probably will have some homework problems that do involve some inverse trig function integration. But we don't have a direct comparison or issue here. And this is going to be a fairly basic problem for these type of questions, and my 4 examples are going to get more and more difficult as we go through them. And just as a resource, we're going to be using these power reducing formulas for an upcoming problem, but not for this one. Okay, so we don't have a u prime over u situation. We can't use, you know, like this integration formula here for arc sine of u over a plus c. So let's set up a little right triangle and see what we can do with some trigonometric substitution. We have the square root of 25 minus x squared, and when you think of your right triangles, I'm sure you guys don't need to really see this anymore, but your old Pythagorean theorem, a squared plus b squared is equal to c squared. When you have, say, solve this equation for one of your legs, you're going to have b squared is equal to c squared minus a squared, and then b, the length of one of the legs, is going to be the square root of a difference of squares. So this is the measurement, or the length, of one of the legs of a right triangle. So let's get that right triangle drawn, shall we? If we recognize that, then when you do subtraction, of course, you need to have a positive difference. That means that this 25, the square root of this a squared, means that a, if a squared is 25, then a is going to be equal to 5, and that's going to be the length of our hypotenuse. Here's theta, and, well, that means our u squared is going to be x squared, so u is going to be equal to x. Okay, or that x is just a length of one of the sides of our triangle. Now, are we going, oh, and the whole radical, the square root of 25 minus x squared, like I previously just pointed out, is the length of one of the legs of this right triangle. So where does the x go? Do we put the x here, or do we put it here? Well, we want to set up theta again with one of those primary trig functions, sine, tangent, or secant, and that means that if I put my x here, then we're going to have the cosine of theta is equal to x over 5, and that's a co-function or a secondary trig function, and I want to use a primary one. So we're going to put the x there, and this is going to be therefore the square root of 25 minus x squared. And now we're looking at the sine of theta is equal to x over 5, setting up those ratios so that we have the constant in the denominator. We're going to move the 5 over with multiplication. I'm also going to flip the two sides of this equation together and get x is equal to, yes, x is equal to 5 times the sine of theta, and then dx. The whole point of this process is to rewrite this integrand into a form that we can see and more easily integrate. So we're going to remove all the references of x and replace it with references of theta. So we have a dx here. So if x is 5 sine of theta, then dx is going to be, well, the derivative of sine is cosine, and we have 5 times the cosine of theta. So now in a minute we're going to get rid of our reference of dx and replace it with 5 cosine of x. And we have a replacement for x. It's 5 sine theta. Now what we need is a replacement for the radical, the square root of 25 minus x squared. And that was step, let's see here, step 3. Find a trig substitution to eliminate the square root. And you want to set up a trig ratio that again will have a constant as our denominator to make for the simplest substitution. So if we have the square root of 25 minus x squared as an adjacent leg to theta, and our constant is the hypotenuse, well then that's adjacent over hypotenuse, and thus we have cosine. So the cosine of theta is equal to the square root of 25 minus x squared over 5, multiplying both sides by 5, and we've got 5 times the cosine of theta is equal to the square root of 25 minus x squared. And now with all of this, let me get my picture out of the way. Hopefully I don't step on that as I'm teaching. We are going to eliminate all references of x in our indefinite integral. So let's move in over here so we have some room. We're going to have the indefinite integral. Our square root of 25 minus x squared is 5 cosine of theta. Our x is 5 sine of theta. Our dx is 5 cosine of theta over 1 d theta. And I forgot that. D theta when I wrote my dx line. Don't forget that. So we have, and notice too that I'm writing my dx, I've already got fractions written in my integrand, so of course I'm going to do 5 cosine of theta over 1 to make sure my numerators and denominators line up. Well, my 5's are going to cancel out, and we get the indefinite integral of 5 cosine squared theta over sine theta d theta. And I didn't, as I prepared this lesson, I didn't pick the simplest and sort of most obvious problems in our homework. I picked the ones that, as I brushed off my calculus skills, caused me to kind of pause and think a little bit and have a little bit of moment of thought before continuing the problem and ultimately solving it. So here we have another little bit of an issue. Thinking of all of our basic integration rules, I have cosine squared. So I have some kind of inside function being raised to a power, so maybe that would be a u substitution where I let u equal the cosine of theta. Well, then the derivative of cosine is negative sine, and I have a sine, but it's in the denominator raised to a negative 1 power, if you will. Or you could say it's equal to cosecant of theta. So that's not going to quite work. So what I'm going to do is I'm going to bring the 5 out front, and I'm going to use the Pythagorean identity to rewrite cosine squared as 1 minus sine squared. Okay, excellent. Now I have 2 terms in my numerator and 1 factor or term in the denominator, so I can take this and just split it up and write the 5 times the indefinite integral of 1 over sine is, of course, cosecant of theta minus, now again, pulling this apart and seeing the 1 over sine as cosecant, we have sine squared over sine, and that'll cancel out to just simply be sine. And now I have two terms that are easily, you can easily integrate. We have 5 times the integral of the cosecant of theta is negative natural log of the absolute value of the cosecant of theta plus cotangent of theta minus the integral of sine is negative cosine, because the derivative of cosine is negative sine. That's going to change that to a plus. Never forgetting your constant of integration. Now we're going, and I could keep that c inside the parentheses as well, probably technically more accurate, but then we're going to take this 5 and distribute it through the parentheses and just get another unknown constant. So we have negative 5 times the natural log of the absolute value of the cosecant of theta plus the cotangent of theta plus 5 cosine theta plus c. And that is the end of our next example. Example number 2 coming right up. Bam! Oh yes, you in the back of the room. Yeah, thanks for reminding me. Yeah, if you're going to write your final answer, you might want it in terms of the original variable, which was not theta. I have to do the same thing with the u substitution. I don't want to put everything in terms of u and then integrate and then have some new function in terms of u. Okay, so I got too excited and forgot to stop. We have negative 5 times the natural log, the cosecant of theta, cosecant being r over y is 5 over x, plus the cotangent of theta being adjacent over opposite. The cotangent of theta is the square root of 25 minus x, the square root, yes, of 25 minus x squared over x. Plus the 5 times the cosine of theta, which is going to be adjacent over hypotenuse. Plus c. Ah, okay. Other than canceling out those common factors of 5, now we are ready for example number 2. Bang! Now for our second example, we have the indefinite integral of x cubed times the square root of x squared minus 4 dx. And just because we're studying integration using trig substitution doesn't mean every single problem is going to need that, right? So make sure you check the easy stuff first. Maybe this is just a u substitution. You know, let's let u equal x squared minus 4, then du is going to be 2x dx. Okay, well that's not going to work because outside of that power of 1/2, or that radical, we have an x to the third power, not an x to the first. So this is going to also require trigonometric substitution to finish the problem. And now that you saw the previous example, and we have the square root of a difference of squares, you know that this radical is representing the leg of a right triangle. I'm going to step off, and why don't you pause the video, try and do this on your own. There's no real special tricks on finishing this problem. This third and fourth example are going to get a bit more complicated. Review some old integration techniques all together and make sure you're remembering all that stuff. This is going to require powers of trig functions. Let's see. Yeah, let me just step off, pause it, give it a shot, and I'm going to reveal the solution one step at a time. Probably the only thing that's a little bit tricky, I do a little bit at the end. You know, there's a good place to stop the problem, but if you're trying to make your answer match a multiple choice question or in the back of the book, you might be at a good spot and have done everything correctly, but you go to check your answer or match one of the multiple choice questions answers and realize that what you have is not matching, and that's really common when you're dealing with trig functions and radicals, that you might have to do a little bit more simplification to make your answer match one of those multiple choice solutions or the answers in the back of your book or solutions guide. Now at this point, when you have an integrand with multiple trig functions in it, you want to remember the tip that we studied with trigonometric integrals, that if you have a secant and a tangent, and secant has an even power which is positive, you want to save a secant squared and convert the other secant squared, or secant to the fourth, or secant to the whatever power into tangent. So you're going to have tangent raised to a high power, and that tangent function inside an exponent will be your u, and the derivative of tangent is secant squared, which is why you're saving that secant squared factor and converting everything else over to powers of tangent. Alrighty. Now, if this is a free response question, say on a standardized test, or just, if one of my students, if I taught this class live in my high school, this particular subject, I do teach the class, just not this far into calculus, I would be thrilled with this answer. But again, as far as making this match an answer in a solution guide in their back of the book, or if it is a multiple choice question and you had to re-simplify this some more, what you're going to see me do is raise the, I'm going to write this, excuse me, as x squared minus 4 to the 1/2 power raised to the third, and then 2 raised to the third power, which is going to be 8. And the same thing here. This is going to be x squared minus 4 to the 1/2 power, then raised to the fifth. I'm going to do 2 to the 5th power. We're going to then have, obviously we have some kind of factor of x squared minus 4 in each of these terms. We're going to factor out the lowest power. And we're also going to be taking these divisions, these fractions, and factoring out a fraction. Now, if you factor out a fraction, you're sort of effectively factoring out a division. So we're going to cancel, balance that with a multiplication. Like if you're, just like when you're doing the undistributive property, or factoring way back in Algebra 1 and Algebra 2. Obviously, it's just a little bit more complicated here. So we have our 2 cubed is 8, of course. Our 2 to the 5th power is 32. I'm looking at the 3, the 8, the 5, and the 32, recognizing that the lowest common multiple between 3 and 5 is 15. So we're going to take out a 1/15th. And the lowest common multiple between 8 and 32, I'm just pairing those up because they're nice factors to pair up. The lowest common multiple, of course, is 32. So we're factoring out a 1/32. And if you're bringing out those fractions, those divisions, basically, you're going to balance that with the multiplication. So we have a 30, instead of having 15 and 32 in the denominator of that fraction we're bringing out, we're canceling out with a multiplication of 32 and 15 in the numerator. Of course, that all cancels out. We have the lowest power between the 3/2 and 5/2. Of course, when you're factoring out common factors, you always want to do that lowest power. 3/2 is lower, and you're doing that through division. Actually, technically, all of this is division. When you divide by a fraction, it's the same as multiplying by its reciprocal. That's how the 32 and 15 got up there. And we have 5/2 minus 3/2 is equal to 1. And this is this is the most, a pretty simple or simplified version of this answer. Let's move on to example number 3, coming up right now. Bam! For our third example, we have the indefinite integral of x cubed plus 2x plus 1 over x to the 4th plus 4x squared plus 4 dx. Now, I'm looking at the numerator and seeing a degree of 3, and the denominator has a degree of 4. Well, when you take the derivative of a polynomial, the degree drops by 1. So maybe this is just u prime over u. But then why would it be my third example? I'm trying to do more and more challenging problems as we go along. Well, if we let u equal x to the 4th plus 4x squared plus 4, then du is going to be 4x to the 3rd plus 8x, and that's it, dx. Okay, well, that's great, but we're not going to just have a simple u prime over u. We're not integrating, we're not just learning how to integrate the natural log function, or get the natural log function as an answer. But we do have a third degree term and a first degree term, and quite nice and convenient. I did try to make these problems work out somewhat nicely. We have 1 times 4 is 4 and 2 times 4 is 8. So actually we do have a u prime over u situation going on there with part of our numerator, but then we have that plus 1. So what we're going to do here is I'm going to step off and allow you to start the problem as well as turn the heat off so you don't have to hear that humming. And split this up into 2 integrands. The first one will integrate to be give us an answer of the natural log of the absolute value of the denominator, and we're going to have to do a trig substitution with the second integral. Now this isn't the only difficulty we have in this particular problem, so as I reveal the solution one step at a time, I'm going to get to a point like I did before and kind of interject some ideas as we finish the problem. Another reason why I'm showing these solutions one step at a time, besides giving you an opportunity of pausing the video and trying it on your own, is, well, that's my example. And I need to fit all of this work on this 4x8 chalkboard all at once so you have a nice clear picture when we're done of the process it takes to complete this integration. And, well, if I end up running out of space, I don't want to, have all that on camera. So I want to give you a nice neat set of notes. So we have separated our numerator, like I said, into 2 separate fractions with our x cubed and 2x, just introducing a multiplication of 4 and balancing that with the division of 4 so that we have this u prime over u situation going on here. And then we have 1 over x to the 4th plus 4x squared plus 4. Now this ends up being a perfect square trinomial where your factors of, if you have an exponent of 4, an exponent of 2, and then of course just a constant, leading coefficient of 1, and the factors of 4 that add to be 4 is of course 2 and 2. So we just end up with x squared plus 2 squared. Okay, so just because you're learning trigonometric substitution doesn't mean every single problem is going to work like that. Maybe this is my u. Well, if my u is x squared plus 2x, then my du is just equal to 2x. I don't have an x up there to work with that. Pulling over or getting our fancy picture in picture out and thinking, well, maybe it's just a inverse trig function integration situation here. Well, we have the indefinite integral of du over a squared plus u squared, giving us, an arc tangent expression, and addition is commutative, so just the fact that x squared is first is no big deal, but this might be my u squared and my a squared, but we have a power of 2 wrapping all of this together, and if you take this binomial and square it, you get 3 terms and not just 2, so this isn't going to develop into some kind of arc tangent situation. Well, that means that this is going to end up being some kind of we're going to be able to use a trigonometric substitution for this problem, but as you saw in the directions at the beginning of this video, that was going to be working with some kind of the square root of sum or difference of squares, and I don't see a square root symbol here. Well, we need to make that happen, and what we're going to do is we're going to rewrite this a little bit to make it neater for us to be able to use, and also note that when you take a number and you square it, you get a positive answer, and when you add 2, you'll still get a positive answer. We're going to rewrite this. I want to wrap this in a square root symbol, and then balance that with the power of 2. Now, squaring and square rooting effectively acts as an absolute value function, but this is going to, this is always going to give us a positive answer anyway, so it's just a different look, if you will, and make this allow the sum or difference of squares here underneath the radical to show up. And we have x squared plus 2, introducing that square root, but we're going to balance that with a power of 2. Now, of course, we still have that original power of 2 that was wrapping this denominator all up in the first place. So let's do another set of parentheses and another power of 2. And that's dx. Now, again, I am just making this look different. With a square and square root being inverse math operations, they just cancel each other out. And again, they're acting a square root and a square together acts as an absolute value function, but this expression would never be negative in the first place, so the absolute value function is kind of not really changing anything. And then here's our original power of 2. So now we have a square root of x squared plus 2. Now that means our a is going to be the square root of 2, and our u is going to be x, and the square root of x squared plus 2 is going to represent the length of the hypotenuse of our right triangle that we're going to set up to do our trig substitution. So I'm going to step off and continue to reveal this solution one step at a time. I'm going to do my triangle work over here and hopefully have enough room on the board to complete our problem. Okay, so I'm showing you every little tiny step for learning purposes. After relearning my calculus after 20 years, mainly on my own, and with the help of a teacher or two at my school that also teaches calculus every once in a while, I don't want to ask them too many questions. They have their own job to do. I do find it frustrating when you're learning a brand new concept or relearning a brand new concept, and you're seeing you look up the solutions guide even, and like there's like 3 steps of work, and you're like, well, how did it get from the second line to the third line? There seems to be a lot going on there. So I'm showing you all those steps that I need and that hopefully is helping you understand what's going on here. So we, had that square root of x squared plus 2, which was square root of 2 secant theta, and we ran it through a couple of powers of 2, or basically raising it to a 4th power, and we're here. And inside the power of 2, we have the cosine function. So maybe my inside function is cosine, the derivative of cosine is what? Negative sine. And, well, I don't have a u and u prime situation here. So this is where we're going to be using those power reducing formulas to rewrite this into an expression that we can continue to work with. So we're going to rewrite the cosine squared theta as 1 plus cosine of 2 theta over 2. Only when I go into the next line, I'm going to write this as 2 separate terms as 1/2 plus cosine of 2 theta over 2. Okay, now in my next example, my last example for this lesson, we are going to use those power reducing formulas again, and I'll handle this a little bit differently in that example to give you a different look. But we have a cosine of 2 theta, and that means that inside the cosine function we have inside the cosine function we have a function of 2 theta. So this is like our u, and u prime would be 2. So I need a multiple of 2 here to complete the chain rule and complete this integration. And what I want to do is I want to multiply, in this particular instant, I'm going to multiply a 2 into both of these terms and balance that by dividing by 2 out front. So I'm effectively multiplying by 1. I'm just changing the look. So I'm going to multiply each of these terms by 2, and of course that's going to cancel out to be 1. And then balance that multiplication of 2 with the division of 2. And we're multiplying by 1/2, and 1/4 times 1/2, of course, is 1/8. And now we have now a couple of terms that are, we can very easily integrate. The integral of integrating with respect to theta, the integral of 1 is theta. And then here, the derivative of sine is cosine, so we're just going to integrate this and have plus 1/2 sine of 2 theta because we have our u and our u prime. Well, this is what you get when you're doing it live. Yes, I'm integrating the second term, but why don't I run the first term through the integral? Because that's just u prime over u. So let me fix that. Okay, great. So now I just need to get my thetas out of here and put it back in terms of x, like my first term is. but that's a little bit of an issue because we have the sine of 2 theta here, and we only have basically equations set up in reference to just theta. Well, yeah, we have a double angle for sine. It's the sine of 2 theta is equal to 2 times the sine of theta times cosine of theta. And of course that means that the 1/2 and the 2 are going to cancel out, giving us this line. Great. Now we're ready to get rid of all of our references of theta, but another difference between this example and the previous two is, yes, we have a sine theta, and that is going to be, x over the square root of x squared plus 2. We have the cosine of theta, which is going to be square root of 2 over the square root of x squared plus 2. But this is the first time where we've had just theta by itself. And here is where we come in and go to work with our tangent of theta is equal to x over the square root of 2, that original trig ratio that we started setting up. We're going to just do the inverse tangent to both sides and see that theta is equal to the inverse tangent of x over the square root of 2. And then just multiplying those two terms together, we have finally let me just double check my work, because it's not like this is a super simple question here. Oh, well, yes, let's go ahead and close that parentheses. And the last thing I'm seeing here is, since it's square root of 2 over 8 times these two terms, just to match up my notes, we can go ahead and distribute that and get 1/4 times the natural log of x to the 4th plus 4x squared plus 4 plus square root of 2 over 8 times the inverse tangent, or arctangent. Here we have the square root of 2 times square root of 2 is 2 over 8. 2 over 8 is equal to 1/4, so we have plus x over, because that 2 is canceling out with the 8, 4, I'm going to go and leave this in parentheses, 4 times x squared plus 2 plus c. Whew. Okay, so yeah, these problems get a bit complicated. We got one more example, and it is going to involve completing the square to get, some kind of expression underneath the radical set up for that sum or difference of squares. And this time we actually are going to be working with some inverse trig functions, getting those as an answer after integrating. Thank you for watching. Bye! It's the last example, and I misspoke a little bit there. We're not going to actually do any kind of integration of inverse trig functions. I just had a note on my notes that it says inverse trig function, and I just glanced at it. It's going to be that having to figure out a replacement or substitution for theta, like we did in the last example. And actually, I just included this example as my last one because we didn't do any problems yet of having to complete the square to get the denominator into a format that's going to allow us to do the problem. And we will have a little bit more complicated appearance or values or expressions for u in this particular problem. But actually, beyond that, it's going to be very similar to our previous example. So we'll get this started, and then I'll step off and, like I've been doing the previous three, reveal the solutions one step at a time. Okay, and again, we don't have a u prime over u situation, because if this is u, then du would be 4 minus 2x dx, and our numerator does not have a degree of 1, it has a degree of 2. So we're going to work on completing the square to get the expression that's underneath the square root symbol to look like that something where it's a sum or difference of squares. And you cannot complete the square unless, of course, you guys know we're in calculus, unless the leading coefficient is positive 1, not negative 1. So we're going to factor that out. Leave ourselves more room to write. Half of negative 4 is negative 2, or just half of 4 is 2. Go ahead and square that. We're going to add by 4, which of course we have to balance by subtracting by 4, except we have to take into account the negative that we factored out, so that plus 4 minus 4, but the minus 4 outside has to get multiplied by negative 1. Now, we're going to have negative 4 times negative 1, which is going to be positive 4, so I'm going to go ahead and put that first. And of course we know completing the square sets up perfect square trinomials. So we have minus, and then we have x minus 2 squared dx. Oh, and all of this is underneath the square root. So we have a difference of squares, or the square root of a difference of squares. So this is going to be my a squared value, or a is going to be 2, and this is my u squared value, so my u is going to be x minus 2. So at this point, we'll be doing some power reducing formulas, and that's pretty much it. It's just everything that we've already included in the previous 3 examples are going to be in this one, so I'm going to reveal the solution like before, one step at a time. I hope you get it right. Stop! Try it yourself first. So now that we have applied the power reducing formula to get rid of or rewrite the sine squared of theta into 1 minus cosine of 2 theta over 2, or have it in separate terms like I have here, instead of, like I did in the previous example, go, oh, well, this is 2 theta, I need a 2 here, so I'm going to multiply all these terms by 2 and then show a division of 2 out front, I'm going to just do it with this individual term and introduce a multiplication of 2 here and a division of 2, and effectively just multiply that term by 1 instead of changing all of the terms in my integrand like I did in the previous example. So just to recap this one more time, with the square root of 4 minus x minus 2 squared, with a difference of squares inside of a radical, we know that that radical, that square root, indicates the side of a right triangle. The square root of 4 is going to be 2. That's going to set up our hypotenuse. And then that u, the x minus 2, is that going to be on the vertical leg or the horizontal leg? Well, if you put it on the horizontal leg, remembering that initial trig function needs to be a primary function, you don't want to do the cosine of theta is equal to x minus 2 over 2. You want to use a primary sine, tangent, or secant. So the x minus 2 goes in the vertical leg, and the sine of theta is equal to x minus 2 over 2, and then we just go from there and start running and find the dx and find a substitution for our square root, and plug everything into our integrand, or changing it from variables of x, removing all those references and replacing them with references of theta, and then just start allowing the algebra to take place. Again, we had that power reducing formula there. Yeah, I just used a double angle identity again to write that sine of 2 theta as 2 sine theta cosine theta. And these two terms here, they were both negative, and both of these first two terms had a factor of the square root of 4 minus x minus 2 squared, the square root of that. So we factored that out of each of those terms. Both of these terms have a division still of 2, a factor of 1/2. So we factored out that common factor of 1/2 and went ahead and, because they were both negative, took out a negative 1/2. And that leaves us with x positive, or just x minus 2 without that negative out front requiring a set of parentheses. X minus 2 and negative 8 over 2 divided by negative 1/2 gave us a positive 8. Negative 2 plus 8 is equal to 6. And that is pretty much it. Oh, and then just we had our 6 theta there, so I underlined that in red, remembering that as you're trying to now go back into references of x and get the answer with the, back in the independent variable or the variable of the original integrand, in this case x, you want to say, oh, I have a theta here, not a sine theta, cosine theta. Go back to your original trig function, the sine of, the tangent of, the secant of, and get that in terms of theta. And of course we have arc sine, and inverse sine means the exact same thing. I'm Mr. True. Oh, before I close this out, I'm going to have another video following this one of doing these types of problems when they are a definite integral. Really kind of just going to, I'm not going to do, I would suggest with definite integrals not rewriting, when you have a lower and upper limit that's referencing x, not to write new lower and upper limits in referencing theta. Just kind of basically go off to the side, do this indefinite integration process, and then when you get it back in terms of x, then you can go and remember that we had a lower and upper limit on our definite integral. So really, you really should not have any problems with those, but when I do release that video, this example, I'm pretty sure, I'm trying to remember if it had anything interesting in here. I don't see any kind of, integration by parts or anything like that. It's just making sure that you know how to deal with those lower and upper limits. We are also going to have a video proving one of the special integration rules. If you happen to have a few of those in the section of your book, to do that proof, you have to do integration by parts. And I have a video covering, and it's titled Integrating Inverse Trig Functions. And I've had some viewers on YouTube annoyed or claiming, basically telling me that I mislabeled my video, but I labeled that lesson with the same kind of section title that my book uses. They were looking for integrating when there is an inverse trig function in the integrand. Well, at the end of, this section we're doing right now, using trig substitution, I did find a couple of problems in my calculus book that involved or had within the integrand an inverse trig function. So I'm going to use those as an inspiration for an example, and that video is coming up as well. So I'm Mr. True. Go do your homework.